We now talk about electromotive force. So you know delta V is equal to IR, where R is the resistance and I is the current in the circuit. Now suppose this delta V is provided by a battery. Now in practice, this battery will also have some internal resistance. So this battery has internal resistance. So let the internal resistance be small r. So let us draw some figures to understand it. So first we just have a normal circuit. We ignore the internal resistance of the battery. So this circuit looks like this. You have the resistance, you have a battery, and there is current going through the circuit. So this is resistance R, this is delta V, and there is current going through the circuit. And we wrote down delta V is equal to IR. Now we are talking about a battery which has internal resistance. So you again draw the battery, but you also draw small resistance next to it, which denotes the internal resistance of the battery. And you copy this resistance R as such. So this is the resistance R, this is the small resistance R, and this is delta V. And the current is still flowing from positive side to negative side. So notice for the battery, it's denoted by two edges. The bigger edge is the positive side. So I have marked the battery now in red. So this is the battery with internal resistance small r. So this is battery with some internal resistance. Now because of this internal resistance, there is a drop in potential. So when the current will move through the battery, it will lose some potential. So the potential it will lose is I times R. So delta V minus I times R is now equal to I times capital R. So delta V now becomes I times R plus small r. So this delta V we write as this curly E, which is electromotive force. So this means it is the maximum possible voltage that a battery can provide. So let us see all these elements playing out in a figure. So let us label this diagram first. Call this point A, B, C, D, and then E. So let us see how the potential changes when we go through these points. So we will see this in a graph. So we have drawn the circuit in the graph. So we will start at D and end at D. So I have opened the circuit. So you start at D, you are at 0 because you are at the negative potential. So you are on the negative side of the battery, so potential is 0. At point E, you have just gained the potential delta V. So you have gained the potential delta V. So this is the total potential you have gained from moving from D to E. Now from E to A there is no resistance, so you have the same potential from E to A. Now at point A you encounter resistance R. So the potential now will drop once you reach point B. So the potential drop, you can see this potential drop is I times capital R. So current times the resistance. So between A and B there is a potential drop. Now between B and C there is no resistance, so the potential remains the same between B and C. Now again at C you encounter resistance small r. So let me just quickly label it. So at C you encounter resistance small r. Now when you cross the resistance, you will again encounter a potential drop, and you will reach point D, that is the negative side of the battery, and the potential now becomes 0 again. So this drop in potential is I times small r. So now you can see from the figure that delta V is equal to I times capital R plus I times small r. So you can check this formula.